This is what we discussed last class. So you have a truss problem. So for a truss, so what you have to identify for a single element. So your stiffness matrix is AE by L C square CS minus C square CS. So this is what your matrix term. And whatever we call C is nothing but cos theta, which is x2 minus x1 divided by L. And S is your sin theta, which is y2 minus y1 divided by L. To identify your length L, we can use 2-point formula, which is root of x2 minus x1 the whole square plus y2 minus y1 the whole square. And similarly, to identify your stress, so we can use this formula, so which is E by L minus C minus S CS. So the location of your displacements for nodal point 1 and nodal point 2. So this is what we discussed, and we discussed about the procedure, how to solve that problem. One problem, we explained everything. So let me consider, additional data, and we consider that, so this stress is horizontal, right? If I consider your stress is horizontal, so what happens? So you can able to see that you have ux1, right? So that is possible. Similarly, you will have ux2, which is possible, right? So you know that. So when you are writing this equation, so we write like this. So we write for nodal number 1, right? We have 1, 2. So x and y. Nodal number 2, we have the other 2, right? So 3, 4, right? So here you can able to see that x1 deals with addressing 1 and x2 deals with addressing 3. So if it is horizontal, let me consider your problem, your truss is horizontal. So which one you will have, C or S, cos theta or sin theta? Yeah, very good. So you will have only cos theta. So which means horizontal means you will have only cos. So cos is meant for horizontal line, right? And of course, sin is meant for vertical line. Okay. So in that case, so you have C, right? Only C, which means C square. So and of course, your C value will be 1 because it is horizontal. So in that case, what you will get, this formula will be changed accordingly. So you will get 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, 0, 0, 0, 0. This is what we will get. So think about it. You know what is the formula for your bar element. What is the bar element formula? It is AE by L, 1, minus 1, minus 1, 1. In this truss, you have 1 and 3, which is denoting. So this is 1, 2, 3, and 4. Only 1 and 3 is denoting. In that case, we can able to see that this formula is changed. So 1, minus 1, minus 1, 1. It is nothing but AE by L, 1, minus 1, minus 1, 1. Right? So the formula is just interlinked with your previous bar problem. Right? Your truss problem. If I make it in horizontal, you will have a bar problem. Right? It is similar to that. Okay, but anyway, so we are going to apply in a truss way, right? Because some will be like this and other will be in other side, right? And it is difficult to identify the addressing point, right? So you consider this as a single formula. Either it's horizontal or vertical, you follow it accordingly. One thing you have to notice, for horizontal line, your C will be 1 and S will be 0, and your length is nothing but the length of the element, whatever it is. And if it is a vertical, your S is 1 and C is 0, and length will be according to that, whatever measurement you can consider that as a length, right? So this way you can simplify your formula. So no need to use this formula x2 minus x1. Don't apply these things. Directly you can identify. So we have a problem here. So you have 4 elements which is connected with 4 nodal points, right? So your Young's modulus is given, your area is given, everything is given. You have to identify what is the around stiffness matrix, global stiffness matrix, and what is your nodal displacements, right? So let us solve this one by one. So by using the procedure, right? The first step is identifying your uh, what a nodal connectivity and what are the elements. So you have four elements: element 1, element 2, element 3, and element 4. And you know how it is connected. Element 1 is connecting element 1 and nodal point 1 and 2. Element 2 is connecting nodal point 2 and 3. So something like this. Okay. So for this, let us make a table. So let me show a table here. So I am just noting what are my elements, right? So element 1, element 2, element 3, and element 4. And according to the connectivity table, I have to say which one is first node and which one is second node, so that when you assemble it, it will be according to that. Then what is the length of the element and what is your cos theta and sin theta, right? You have as a table like this, right? So let us identify one by one, right? Let me consider element 1. So element, it is mentioned already. No need to worry about it. So since it is mentioned, you have to write that accordingly. Don't change your element numbers. Okay, because the key will be based on this. So if it is not mentioned, you can take anything as element 1. So even 4 you can consider as element 1. It doesn't, no need to worry about it. Okay, so here I'm going to fix this entire setup in first quadrant. So in that case, I will consider this. This is my x-axis and this is my y-axis, right? So which means this will be 0, 0. This point will be 0, 0. Similarly, what is your 2? So this is 1000, 0, right? What is your 3? So 3 is 750 here. So this is 1000, 750. And what is your 4? 0, 750. So this is my nodal points. So location of your nodal points. Now we will proceed one by one. Element 1, I will consider first node is 1 and your second node is 2. So element 1 is connecting nodal point 1 and 2. What is the length? So length, we have the formula. So what is the formula? Length is equal to root of x2 minus x1 the whole square plus y2 minus y1 the whole square. This is the formula, right? But no need to apply when it is when you have a horizontal or vertical, right? So directly you can write. So your length is 1000. You know that. Directly I will write as 1000. So this is L is 1000. As we discussed earlier, the your length, your element 1 is horizontal. In that case, you will have only cos theta. You don't have sin theta, right? So in that case, I will get cos theta as 1 here and sin theta is 0. So let me consider your element 2. So when I consider your element 2, so you can consider the first node accordingly. So I will consider this as my first node. So 2 is my first node and 3 is my second node. So what is my length? So you'll get 750, right? So length of this element is 750. Directly I will write. Vertical. So since it is vertical, you know that your theta is 0, cos theta is 0, and your sin theta is 1. Okay, directly I am writing this. Okay, so be careful in this. The problem here is always you consider the minimum point this as the first one and the other one as a maximum point. So that is second node. Don't take an opposite direction. If I consider this as 1 and this as 2, what happens according to the formula? What is your sin theta? Sin theta is y2 minus y1 divided by L. Right? So what happens? This will be y2. This will be y1. Right? So we'll get sin theta as S minus 1. So always you consider along this direction. So left to right. Your nodal points, first node should be left hand side. Second node should be right hand side. Similarly, bottom to top. So first node should be bottom side. The second node should be the top side. So if you do that, no need to worry about this. This will be positive values. Otherwise, it becomes negative. Okay, be careful in that. So while doing this shortcuts, okay, if you have any confusion, you can directly do it. No problem. So you solve one by one. Each one, you identify what is your formula based on the formula. What is your cos theta? What is your sin theta accordingly? Then substitute it here. Okay, both is possible. So next, let me consider your element 3. So element 3 is this. My left side node is 1 and my right side node is 3. So I'll consider 1 and 3. Here, I can't able to identify my L because it is inclined. Okay, so what I have to do, I have to use that Pythagoras theorem or the formula, whatever is just given here, right? So let us apply the formula, right? So you know, so this is my element. So element 3 is like this. So this is 0, comma 0, and this is 1000, comma 750, right? In that case, x2 minus x1, root of x2 minus x1, so 1000 square plus, so y2 minus y1 is 750 square. So what you will get? So root of 1000 square plus 750 square.
So 1250, sir.
Okay, thank you. It is 1250. So we'll substitute 1250 here. And what about your cos theta and sin theta? So cos theta is x2 minus x1 divided by L. So x2 minus x1, x2 is 1000, x1 is 0, divided by L is 1250. So what is your sin theta? Y2 minus y1 divided by L. So which is 750 divided by 1250. So what are these two values?
So 0.8 and 0.6, sir.
Okay, 0.8 and 0.6. Thank you. So you are getting 0.8 here and 0.6 here. Right? So this is over. Next, we will proceed with your element 4. So if we go for element 4, your left side node is 4. So that will be my first node. Right side node is 3. So that is my second node. Okay, so 4 and 3. What is the length? 1000. It is horizontal. So if it is horizontal, of course, cos theta will be 1, sin theta will be 0. Right? So this part is over. So this simplifies your work. Okay, so that you can easily locate your element stiffness matrix. Okay, so now we identified what is your length, what is your cos theta, sin theta, everything is over. Now we'll proceed with your element stiffness matrix. So whenever you write this, you have to draw that element. Okay, that is very, very important. So that carries some marks. So this is connecting 1 and 2. So element 1, what is the K formula? So K formula is A by L, right? So C square CS CS S square. So same thing. So minus C square minus CS minus CS minus S square. So C square CS CS S square and C square CS CS S square. So this will become negative, right? So this is my K matrix. Okay, so I'm going to arrange this and I'm going to substitute it. We already know. So I will write what is my C for this, right? So what are the data we required here? So these are the few data which is required. So what is your area? Area we know which is already given. So area is 6 to 5. So area is 6 to 5. Young's modulus 20 per 5. I think 20, yeah, 20 per 5. L length we identified already in the table, which is 1000. C, it is 1. Yes, it is 0. So these are the data. So we are going to substitute. Okay. So for my convenience, I will change this to some other view. So I think you can able to see some squares, right? So the old method, right? So let us solve this so that I can able to match it accordingly, right? Okay. So let me go for your K. So I'm going to deal with K12, right? So this is my table. So we have 4 cross 4 matrix, right? So 1, 2, 3, 4. Okay. So C square is of course AE by L, that is common term. Sorry, I have not considered that. So AE by L. So A is 625 into 2 into 10 per 5 divided by L is 1000. C square So C square will be 1, right? So because wherever you have only C, that you will have value, others will become 0. So this is 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1, 0, and remaining terms also 0, right? So this is my value. So multiply this, what you are getting when you multiply all these things, all these terms.
So 1.25 into 10 power 5, sir.
Okay, you are getting 1.25 into 10 power 5. Thank you. So in that case, I will take this 1.25 inside. So I will take 1 into 10 power 5 outside. Right? So I will rewrite my K. So K12, right, which is equal to 1 into 10 power 5. So remaining terms, so you have 1.25, 0, minus 1.25, 0, 0, 0, 0, 0, minus 1.25, 0, 1.25, 0, 0, 0, 0, 0. So this is my term. So let me address this. So that is also very important. Now also we can do that. So addressing is connecting nodal point 1 and 2. So nodal point 1 we have ux1, uy1. Nodal point 2 is ux2, uy2. So again ux1, uy1, ux2, uy2. Right? This is my first thing. Right? So first element is over. Let me go for the second element. Element 2. So we'll go for element 2. So when you go for element 2, your matrix, so you know that. So your element is like this. It is connecting 2 and 3. Right? Nodal point 2 and 3. And your A is same, which is 625 mm square. E is same, which is 2 into 10 power 5 Newton per mm square. L is 750 now. And what is your C and what is your S? C is 0, S is 1. Right? Because your second element is vertical. So based on that, so your C is 0 and S is 1. So we got this. Now we'll proceed. Same formula. So I'm not going to write this thing directly. I will substitute it. Let me write it out. So this is equal to 625 into E is 2 into 10 power 5 divided by 750. Right. So this one C square. C square is 0. So wherever you have C, you put is only S, it should be value. So this is 0, 0, 0, 0, 0, 1, 0, minus 1, 0, 0, 0, 0, 0, minus 1, 0, 1. So this is my data. Okay. So I got this value. Right. So the next step, what I can do is I will multiply this. Let us identify what is the value here. So just multiply and tell me in terms of into 10 power 5. Okay, 1.667. Okay, right. In that case, you will take that 1.667 alone inside. You'll get 0, 0, 0, 0, 0, 1.67, 0, minus 1.67, 0, 0, 0, 0, 0, minus 1.67, 0, 1.67. So this is my matrix. And 1 into 10 power 5 is a common term. This K connecting nodal point 2, 3. So what is the address here? So address is different. So connecting nodal point 2 and 3. So UX2, UY2, UX3, UY3. Similarly, this is also UX2, UY2, UX3, UY3. So this is my address. So let me go for element 3 now. So element 3 is inclined. So I can able to see it is inclined. So something like this. This is my element 3. Connecting nodal point 1 and 3. So our area is the same 625. Young smallest is 2 into 10 by 5. No change. Your L is different 1250. So based on this, in tabulation, your L is 1250. C is 0.8 and S is 0.6. So C is 0.8 and S is 0.6. So this we have to substitute. Okay. So in that case, so this is my K13 is equal to 625 into 2 into 10 power 5 divided by 1250 into, so this is my matrix, right? So C square, so which is 0.8 square, CS, so 0.8 into 0.6, again CS 0.8 into 0.6, this is S square, so 0.6 square. So same will be repeated here accordingly, right? So before that, I'll put X here, so then I will substitute it accordingly. Okay. So, right. So what is your 0.8 square? 0.64. What is 0.8 into 0.6?
0.48, sir.
0.48. So this is 0.48. And this is 0.36. Right? Okay, let it be. So now, what about these things? How you multiply this? What is the value here? Okay, you are getting 105. Right? Let me proceed. So I will write my overall matrix here. So K13 is equal to 105. Value here is 0.64. Right? So the next one is 0.48. This is also 0.48. This is 0.36. Same thing. So minus 0.64, minus 0.48, minus 0.48, minus 0.36. Sorry. So this also. So minus 0.64, minus 0.48, so minus 0.48 and minus 0.36. So this is 0.64, 0.48, so 0.48 and 0.36. So addressing, so it is connecting nodal point 2, so 1 and 3. So ux1, uy1, ux3, uy3. Similarly here, ux1, uy1, ux3, uy3. So this is my address. So you can see how complicated it is. So it's a time consuming process. Only thing what we can do is we can also go in other way, like filling only your upper triangle. Okay, now we'll go for the next element, element 4. Look at this element 4. So you can see that element 1 and element 4 both are similar because your L is same, your SC and S is also same, right? In that case, whatever the stiffness matrix for element 1, that can be used again for element 4. So what I'm going to do, just I will copy the same stiffness matrix which is applicable for element 1, right? Only the address is changing. Okay, so here I will write this is element 4. Okay, so what is this element 4? Element 4 is connecting nodal point. First node is 4 and 3. So it is connecting 4 and 3. So in that case, you will get ux4, uy4, ux3, uy3, right? Indicating 4 and 3. So ux4, uy4, ux3, uy3. These are my matrix. So this part is over, right? We identified all my element matrices. Next step is identifying global stiffness matrix. What is my global stiffness matrix? Right. So first we have to identify what is the size of my global stiffness matrix. What is the size? So you know the formula, right? It is number of nodes into degrees of freedom per node. So number of nodes into degrees of freedom per node. So how many nodes we have here? So we have 4 nodes, and each node is having a degrees of freedom of 2. So 4 into 2, right? So which means 8. So my matrix is 8 cross 8 matrix. Okay. So the size of my global stiffness matrix is 8 cross 8. Okay, that is what we are going to consider. So okay, let me go for the global stiffness matrix K. So this K matrix is having a common term. What is that common term? It is 1 into 10 power 5. Right? So 1 into 10 power 5 is a common term. Right? Remaining, what are the things? So I will call this as ux1, uy1, addressing this. ux2, uy2, ux3, uy3, and ux4, uy4. Right? This is my overall term. Right? So similarly, so I will consider the same thing. Right? So 1, 2, 3, 4, 5, 6, 7, 8. Should I have here? Right? So this is my overall matrix. So similarly, I will write it at the top. So what are the terms? So this is ux1, uy1, ux2, uy2, ux3, uy3, ux4, uy4. Sometimes in some books, instead of this ux1, uy1, they will also call it as u and v, right? X, they will call it as u, y, they will call it as v. In that case, what they will write is u1, v1, u2, v2, u3, v3. So if you are convenient in that, that also you can follow. Doesn't matter. Okay, now we addressed it. Only thing is I have to fix this. So we start with element 1. So if I consider element 1, so element 1 is connecting 1 and 2, right? In that case, this terms you will be getting. So 1.25, 0, minus 1.25, this thing, right? So I will write it here. Okay, so I'm going to write only the upper triangle, right? So this term, I'm not going to write the lower triangle because don't want to waste time, right? Only this term I'm going to write upper triangle, whatever is just on the top. Okay, so let me write it accordingly. So you have 1.25 minus 1.25, so something like that. So 1.25, 0 minus 1.25, right? And this one is 0, right? This is all zeros, 0, 0, 0. And here also minus 1.25, 0, 1.25, 0. So this is my term. So just look at here. So this is similar to that, right? So that's why we can verify this also. So this is what you will get. Okay. So this term is also 0. Okay. So u1, x1, u1, y, u2, y2, right? So up to this, right? So this overall term is over. Then we go for element 2. So when you go for element 2, you have x2, x3, right? 0, 0, 0. So you have only in this term. So uy2, right? And uy3. So something like that, right? So let me substitute that. Okay. So it is ux2, ux2, x2. So this coordinate is 0, right? So which means where is that x2, x2? So x2, x2, this is 0, 0, right? And this is again 0, right? 0, 0. And this has to be 1.25. So sorry, 1.67, 0 minus 1.67, right? And this is 0, 0. And the last it is 1.67. So this is what your term is, right? So your element 2. So element 2 is having 2 and 3. So I am assembled based on 2 and 3. Okay, this is over. Next, with element 3, it is connecting x1, 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 y1, something like that. So in that case, so you just put it accordingly. So which one is x1, x1? So this is 0.64 plus 0.64, this case. And x1, y1, this is 0.48 plus 0.48, right? This is x3, x3, x1, right? Minus 0.64. And y3x1. So this is y3x1 minus 0.48, right? Similar this one, y1, y1. So this is 0.36, right? So you don't have this x3, y1 minus 0.48. This is minus 0.36, right? Similarly, this one. So x3, x3. So where is x3, x3? x3 is here, x3 is here. So this is the term. So x3, x3 is 0.64 plus 0.64. And x3, y3 is 0.648, right? X3, y3. So 0.48, right? And last y3, y3, right? Y3, y3. So y3 and y3. This is 0.36. As I told you, I am concentrating only on upper triangle, not on the lower triangle. So here also you concentrate only on the upper triangle. Don't concentrate on lower triangle, right? So it is easy for you to assemble. Right, this part is over. Next, we'll proceed with last element, which is connecting 4 and 3. So x4, x4, right? x4, x4. Where is x4, x4? So x4 and x4 is here, right? This is 1.25, right? So x4, x4, y4, x4, 0. So y4, x4 is 0. So y4, x4 is 0. And y4, y4 is 0. So y4, y4 is also 0 here. I put 0, right? So these terms are over. Next, this term, which is x3, x3. So x3, x3 is 1.25. So that is the value. So 1.25, x3, x3. So where is x3? x3, x3. So 1.25, right? So what about this minus 1.25? So x3, x4. x3, x4. Sorry. So it is x3 and x4. Here it is x3, x4. So minus 1.25. So x3, x4, right? So that's the term. So I think you have only these three terms. Other things you don't need to worry about it. So that completes this overall uh, assembly of this. So now what I have to do is I have to add it and I have to consider that as a global matrix. So now what we can do is I'm going to write this again. So in the next step, but I will use some shortcuts, right? What is the shortcut? So I have to utilize the time accordingly and reduce my work, right? So what to do? So already I written only half of the matrix, right? Because it is symmetry, right? So that reduces some time. The other one is now itself you can eliminate whatever which is not necessary, right? So let me look after the question. So this is my question, right? So this question is having something with having model points 1, 2, 3, and 4. Now my aim is I don't want to look after the particular nodes which is already fixed, because what we will do, so whenever your node is fixed, we will eliminate the first column accordingly, and we are not going to use it for our equation, right? So that's why, so now itself we can eliminate, no need to calculate all these things and no need to write it. So you can just put x, so whichever which is eliminated, right? So I'm going to do that. So for that, what I can do, let us identify what is my boundary conditions here. So if I look after this boundary condition, you can able to see that your nodal point 1 is fixed. So if 1 is fixed, you know that ux1 and uy1 both are zeros. So which means it is fully fixed, right? So I no need to look after these things, which is ux1, uy1. So I can eliminate these columns, right? So next, similarly, element 2, so sorry, nodal point 2, if you look here, it is having a roller support. It means that your ux is free, but y is fixed. So which means uy2 is fixed here, that is 0. ux1, you have a value. We don't know what is that. So sorry, ux2, you have a value, which we are going to identify later. So 3 is no fixing here, so which means you have all the values here. 4, it is fixed, which means ux4 and uy4. This also zeros, right? Because it is fixed on both the ends. So what I can do now itself, I don't want to write this, whatever the components related to this. Okay, so which is x1, y1, y2, x4, and y4, right? I can eliminate it. So let me look after that. So this is my matrix. Okay, right. So what I'm going to do is I'm going to write this. So you know what is my terms. So this is ux1, uy1. So this is x2, y2, x3, y3, x4, y4. Similarly, when you write it in column row wise, x1, y1, x2, y2, x3, y3, and x4, y4. So now itself, I can cancel whichever which is not required, which is x4, y4. So this two, no need to write these values. Leave it. Similarly, y2, so y2 row and y2 column, you can leave that. Similarly, x1, y1 rows and x1, y1 columns, right? So what are the remaining terms you have? Be careful. So this term, right? So which is having x2, x2, right? So what is x2, x2? So x2, x2 is 1.25. So you have 1.25 and x3. So x2, x3 is having, so you have the value x2, x3. It is 0. x2, y3 is also 0. So these two terms are 0. So this is 0, 0. And x3, x2. So what is x3, x2? Of course, you know that x2, x3 is 0. So x3, x2 is also 0. So you can directly write, even though it's symmetric, anymore, I'm not going to consider. Next, x3, x3. So what is x3, x3? So it is 0.64 and 1.25. So we're getting around 1.89, right? So we're getting 1.89. So x3, x3 is 1.89. Okay. So next, x3, y3, right? Which is 0.48. So this is 0.48. Okay. So next, so x4 is our goes out, so no need to worry. So last one is x4, y4. Sorry, I think y3, y3, right? y3, x3 is similar. x3, y3 is 0.448. So y3, x3 is also 0.48. So what is y3, y3? So that one we have to identify. So when you look here, so y3 is here and y3 is here. So it is 0.36 plus 1.67, 2.03. So we're getting 2.03. So remaining terms, you no need to worry because this is what the equation it is going to come. right? So after eliminating, after applying your boundary conditions, right? So either you can put X or you can strike it out like this, indicating that these data are not required. So apply this whenever you have a bigger matrix like 8 cross 8 matrix. Okay, F matrix, I am writing my, what is my force matrix. In nodal point 1, you don't have any force, so 0, 0. In nodal point 2, you have only Fx force, Fy 0. 3, Fx is 0, Fy is negative because downward direction. 4, you don't have force. That I am writing it here. So 4, it is, you don't have force, right? So this is my F matrix. Okay, so in terms of this. And you know that, so this also, it is in terms of x1, y1, x2, y2, x3, y3, and x4, y4, right? You know that as per the boundary conditions, x1, y1 is get cancelled, y2 is also get cancelled. Similarly, x3, y3, x4, y4 is also get cancelled. So remaining term will be there. Okay, so now I will write what is my force matrix. What is my force matrix? F. My force matrix is 10,000, 10,000, 0, and minus 12,000. So this is my F is equal to K. K is 1 into 10 power 5. Remaining term of your K. So what is my remaining term? 1.25, 0, 0, right? 0, 1.89, 0.48. And the last term is 2.03. And this is also 0.48. So symmetrical, so this side is also 0. Into, what is my matrix? X2 is left out, X3, Y3 is left out, sorry. The first term is X2, Ux2, Ux2, Ux3, and Uy3. So these are my terms. Okay. So now we got what is our matrix. So it is in an equation form. Now you can able to write this in equation. So what is my first equation? 10,000 is equal to 1 into 10 power 5 of, so 1.25 Ux2. Then other things are 0. Okay. So other things are 0. You can eliminate it. So in this case, I can able to get what is my Ux2. Can you tell what is the value of Ux2?
So 0.08.
0.08 mm. Very good. So this is the value we are getting here. Next, second term, 0 is equal to 1 into 10 power 5 into 0 into Ux2, leave it. So remaining, so 1.89 Ux3. So 1.89 Ux3 plus 0.48 Uy3. 0.48 Uy3. So this is equal to, of course, that is 0. So which is already indicated. So in that case, what I will get is, I will get something like 1.89 Ux3 is equal to minus 0.48 Uy3 is what I will get. Let me consider this as one equation, equation 1. Last term, so minus 12,000 is equal to 1 into 10 power 5 into 0 into Ux2 is 0. So 0.48 Ux3, 0.48 Ux3 plus 2.06, sorry, 03 Uy3. And this is my equation. Now you substitute this in this equation, find out what is the values of Ux3 and Uy3.
So UX3 is 0.016 and UY3 is minus 0.063.
Ux3 is 0.013.
16.
0.16 mm. UY3 minus
0.063 mm.
0.063 mm. Yeah, thank you. So these are my values. So I got all these values. So UX2 we got, UX3 and UY3. So look at the question. The question is not asking you to identify what is your element stress. So it is up to this. That is enough. Okay. So in that case, so this completes our problem.